Hi, everyone. I'm glad to introduce our newly published work here. It is a novel and effective rectification method for scene text recognition which mainly rectifies the principal regularities. Reading irregular scene text is a challenging problem in scene text recognition. Existing TPS-based rectification methods seek to rectify text images into a strictly regular form via free parametric transformation functions. However, they always suffer from information loss or severe deformation due to their poor constraints to the transformation functions. In our investigation, CNN and attention are robust to many slight irregularities. What inspires us to propose this method to mainly rectify the principal regularities, and leave the slight irregularities to the recognizer? The workflow of our proposed method is divided into 4 modules. The Densities and Orientations Estimating module first estimates the character densities and orientations on a 4-stride map of the input image. With the estimated results, the Curve Fitting module scores the fitness of each curve from a predefined curve set and selects the best fitting one. The Grid Sampling module then generates a sampling grid that neither loses important visual information nor causes severe abnormal deformation and rectifies the input image based on the generated grid with bilinear interpolation. The Sequence Recognizing module finally recognizes the rectified image with a CNNLSTM-attention encoder-decoder. The backbone of DOME is a small down-sample-upsample pyramid architecture. The output of DOME is in 1/4 height and 1/4 width of the input image with 3 channels. A sigmoid function is applied to the first channel to generate the character densities, and normalization is applied to the last 2 channels to generate the character orientations. The annotation for character densities is a map of 1-hot vectors, indicating whether the pixels belong to a character or the background. And annotation for orientations is a map of normalized vectors. By checking a large number of scene text images, we found that the shapes of most scene texts can be represented by quadratic Bezier curves. Therefore, we try to find quadratic Bezier curves to fit the estimated character densities and orientations. Most STN-based methods predict control points from a continuous space, which may lead to unexpected results without explicitly considering the constraints on the control points. Our CFM selects a Bezier curve from a small predefined candidate curve set by scoring their fitness to the estimated character densities and orientations, which makes it simple, yet robust and effective. Given a selected curve, we generate the sampling grid that is vertically centered at the curve. Firstly, it is evenly divided into 256 segments. Generally, for the midpoint of each segment, we evenly pick 64 points over the perpendicular line of length 2 and centered at the midpoint, and take these 64 points as the corresponding column of the output. However, in some exceptional circumstances, such a naive sampling strategy may lose information. We solve this problem by aligning the sampling directions at both ends with 2 vertical sides. Following Aster, we exploit a CNNLSTM-attention-based sequence encoder-decoder to generate character predictions. It consists of a CNN backbone, a bidirectional LSTM with 256 hidden channels, and LSTM-based attention with 512 hidden channels. Lambda is a hyperparameter that influences the performance of curve selection. Our method performs best when lambda takes value from 230 seconds to 830 seconds. Generally, when lambda is too small, many pixels cannot be covered by the sampled points used for scoring. On the contrary, a too large lambda will lead to the decreasing of scoring resolution because many sampled points are overlapped among different curves. We train RPI with synth-text, synth90K, and the collected real-world data. Besides, RPI- is trained with only synth-text and synth90K. The rectification-based methods are trained with only synthetic data. Therefore, we compare RPI- with them. RPI- wins all the other rectification-based methods on Qt80, the dataset specifically built for evaluating curved text recognition, and performs comparably with them on IIIT5K, SVT, IC03, IC13, and SVT Perspective, but is worse than 3 of them on IC15. SAR is the most representative 2D decoder-based method, and note that SAR is trained with real data and extra synthad data. RPI wins SAR on Qt80, IIIT5K, and SVT, and is comparable to SAR on the other 3 benchmarks. Thank you for watching.